Hey everybody, welcome back to chemistry. And now we're moving into a new chapter, chapter 5, which is about chemical reactions. And so eventually what you're going to learn how to do is how to take a chemical equation like this one I have in the board here and balance it. So what you'll learn is to balance an equation, you have to make sure that for every element in the equation, you must have as many atoms of that element on the left or reactant side of that equation as the right and the product side of the equation. So eventually, what I'll teach you how to do is how to make that happen by adding coefficients here to this chemical equation. So what you'll learn eventually is you'll have to put a coefficient 2 in front of aluminum, and you're going to have to put a coefficient of 6 in front of this molecule, which is hydrochloric acid. Then what you'll have to do is you'll have to put a 2 here in front of aluminum chloride. And then finally, to completely balance the equation, you're going to have to put a 3 in front of H2, which is hydrogen gas. So I'll show you how to do that later. But what I need to talk about now is why we balance equations. And so what I'm going to do is I'm going to go through this little presentation. So if I can increase the slide. So for me to talk about why it's important to balance an equation, I think a good thing to do is for me to talk about a particular reaction. So the chemical reaction, which I'm going to talk a little bit about right now, is the burning of natural gas. And so maybe you have seen this before. If you ever say we're in some kind of chemistry lab, maybe the teacher asked you to break out something called a Bunsen burner, and then you turn on the natural gas, and then what you did is you ignited the natural gas and it burned. You got this nice blue flame here. And so this blue flame is occurring because a chemical reaction is going on. What is going on is that you have natural gas, it's reacting with oxygen in the air to produce carbon dioxide and water. Now, one of the things you'll have to learn is that natural gas is actually a particular molecule. It's this molecule here, which is methane. It has one carbon atom in the center, and then there are 4 hydrogen atoms that are stuck to it. So one thing that's kind of interesting is if you tried to burn natural gas in an environment that had only nitrogen and nothing else, you would not be able to ignite the natural gas. It just would not burn, it would not combust. So what that might tell you is for natural gas to burn, there must be something else in air other than nitrogen that is required for the reaction, and that thing is oxygen. So oxygen is also required for the reaction. However, when the oxygen meets with the methane and there's something to start the reaction like a little bit of flame, they will completely react. And so what will happen is when they completely react, they're gone. They completely disappear. And so those things that disappear in the reaction that you had before are said to be the reactants. The reason why they disappear is because in that flame, the oxygen will meet up with the methane molecule. And although the total atoms are still there, they tend to rearrange themselves and they reform new molecules. And the new molecules that they form are carbon dioxide and water. And so these are the products of the reaction. So what we can kind of do is sort of describe the burning of natural gas. You can also call it the combustion of natural gas with this equation. And so I've written out the equation in sort of 2 ways. I've written it out in sort of pictorial form, which kind of helps me out in understanding it. And also I've written it out in terms of the names of the molecules and their formulas. And so what I've done is I'm showing, it looks like we're having methane reacting with oxygen. Those are the reactants, and they will produce carbon dioxide in the water. And as you probably already know, the methane, the oxygen, which are to the left of the arrow, will be the reactants of the reaction. And the carbon dioxide and the water, which are to the right of the arrow, are the products of the reaction. We might want to confirm that the number of atoms for each element is the same whether it's reactants or products, because for really reactions to completely go, we need that requirement. So let's go ahead and do that. So what I've done is I counted up the atoms of each of the elements on the reactant side and then on the product side. So for example, you can see with carbon, that black element, there's one on the reactant side and there's one on the product side. So that's a good sign. Now if you look at hydrogen, there are 4 of those white atoms, the hydrogen atoms, on the reactant side, but on the product side there are only 2, so that may be a bit of a problem. And with oxygen on the reactant side, those 2 red atoms, there's 2 oxygens, but you can see that now in the products, another one seems to have appeared. There are 3 oxygen atoms. So something weird has happened. We really don't have atom balance on the left side versus the right side of the equation. And so it's almost as if, as it's written, that we are actually having hydrogens just kind of disappearing and going off somewhere. And also maybe oxygens are just appearing from nowhere. And so that can't happen. So this doesn't seem to make sense to us. So there's still something not quite right with writing this equation this way. And so what we may want to do is change the proportions of molecules that are reacting such that the atoms for each element are equal on the left side versus the right side of the equation. And so again, I sort of indicated here that as the equation is written with one apiece, and you can see it's written in different ways. These pure substances are written out as words at the top, and then we have an equation with formulas, and then we have pictures. And so what this is a good qualitative description of the chemical reaction, because what a qualitative description is about is it tells you the kinds of molecules that are reacting and the kinds of molecules that are being produced, but it doesn't really have any numbers associated with the description. So this is a reasonably good qualitative description. But the problem is this is not a good quantitative description for the problems that we saw before. We don't right now, as things are written, have the correct proportions of these molecules that are reacting. Now we can change it pretty simply. So if we add in another oxygen molecule as a reactant and we add in another water molecule as a product, then it becomes not only a good qualitative description but a good quantitative description of the reaction. So let me talk about why it's a good quantitative description. So the reason why is, remember beforehand when we had one of each and we didn't really have good atom balance for the elements? Now, then we added an oxygen molecule and a water molecule. What you can sort of see is that for each element, there are as many atoms of that element on the reactant side as you see on the product side. And so for carbon, for example, we're still good with one carbon atom in methane and one carbon atom in carbon dioxide. So we have carbon balance on either side of the arrow. Now let's look at hydrogens. When we added that extra water as a product, we now have a total of 4 hydrogen atoms in the product, which matches the 4 hydrogen atoms in the methane molecule in the reactant. So the hydrogens now balance. Also, when we added that extra oxygen into the equation, now we have oxygen balance. On both sides of the arrow, we have 4 oxygen atoms. And so basically we have a balanced equation. So how do we balance the equation? We just added additional molecules as necessary so that we got atom balance for each of the elements. When you add additional molecules for a particular compound, then you're changing the number of molecules involved in the reaction, and therefore you would change the coefficient in front of the formula. When we have good quantitative balance of the atoms, that is the ratio of the molecules that are reacting. So it's not 1:1 produces 1:1. We now realize that for the law of conservation of mass to be satisfied, we really need 2 of oxygen reacting with 1 of methane to produce 2 of water and 1 of carbon dioxide. Now, you could just add molecules to that. So again, 1 molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. Now, one of the things that we've learned is that there is a direct relationship between moles of a substance and a molecule of a substance. So what you can also say, because moles and molecules are directly related, that 1 mole of methane will react with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. And so what we can do now is write a final equation using formulas. And note what I've done. I've indicated the mole ratios with the coefficients. And so the reason why you don't see a coefficient in front of methane, which is CH4, if you don't see a coefficient there, assume the coefficient is 1. So there's really a 1 there. Also, beside carbon dioxide, there's really 1 there. Okay. And so the coefficients, you can see, are a reference to either the mole proportions of these molecules or the molecule proportions of the molecules.